Hi there, I'm Richard Simmons. I'm a technical director at Rare, and I'm giving you a talk on writing secure multiplayer games, or as I've noted, at least making it a little bit harder for the bad people out there to do bad things to us. Now, we're going to be taking questions all the way through in the comments section. Then we'll address them at the end, just so we don't interrupt the flow of the talk. Do please drop a whole bunch of stuff in there. We will get around to it at the end. Running time on the talk is half an hour, 40 minutes, so we should have plenty of time to go through those. So let's get on with it. First of all, who am I? Why should you listen to me? So, as I said, I'm Richard Simmons. I'm a technical director at Rare. I'm tech director on the engine team. But Rare is actually the first place I've worked on the engine team. Prior to that, I've always been on the game teams, and I started work back at Free Radical Design on the ill-fated Star Wars Battlefront 3. That, of course, has now been rebooted, but 13 years ago, I joined the game industry, and that was the first game I got to start work on. When Free Radical Design went down, we got picked up by Crytek, the makers of the original Crysis game, and we went to work on Crysis 2 and the multiplayer side of that. And then I was promoted to lead developer for Crysis 3 on the multiplayer side. Crysis 3 did a whole bunch of anti-cheat work there. That's where a lot of my knowledge around this area kind of got built up. And then after Crysis 3, moved on to a console version of the original Crysis. And then the good people at Rare came knocking and were interested in me doing work for them. Started off at Rare on Kinect Sports Rivals, very different game. Never done anything with Kinect before, very interesting. Before finally getting to grips with a bit of multiplayer goodness on Sea of Thieves. Midway through Sea of Thieves dev, I also got to spend a little bit of time doing some retro gaming goodness with Rare Replay before finally starting work on Everwild, our upcoming game, which we're working on at the same time as Sea of Thieves. So we've got a good split of development going on there at the moment. So, been working in the industry for about 13 years, the last coming up to 8 years or so at Rare. Lots of networking, lots of multiplayer in there, all that good stuff. So, what is this talk going to be about? This talk is going to be about a whole bunch of things, but we're going to talk through network topologies, which is just how a network is laid out, and the advantages and disadvantages of different layouts. We're going to cover the security of all of those different layouts, and then how people manage to neatly shoot themselves in the foot. Then we'll take a look at some approaches in general terms that are a bit more secure and some of the problems out there that are just unsolved, really. So I will say that there are going to be a whole bunch of caveats and assumptions here. It should be noted, first of all, that these are all rules of thumb. There are some really notable exceptions here. Real-time strategy games typically have very different networking, as do fighting games, Street Fighter and the equivalent. The other thing we're going to be assuming is that the clients can change anything on their box, or they can change any network traffic. What that means is if you're running your game on someone's computer, if someone's running your game on their computer, they can change the memory. They can do really whatever they like. They can change the data they're sending out. They can pretend things have happened that haven't really. You've got to think that once you send a disk out or once someone's downloaded a game, the computer or the Xbox it's on, or PlayStation, that's in the hands of the enemy. They can do whatever they like to that. Now, people might think that actually that isn't realistic. Consoles are relatively secure. But if you actually look back in the past, you'll see there are a number of instances of consoles being hacked. There are well-documented hacks for PlayStation 3 and Xbox 360. And you really can't make the assumption that you're always going to be secure. The best way to write games for multiplayer is to try and make them more secure by default. So there are a whole bunch of different ways of networking games. I mentioned network topologies. Let's talk about some network topologies. Really, it's just a fancy way of saying how the computers are networked. And there are four main approaches here. So peer-to-peer networking, this icon that we have, this diagram we have over on the left, this is where every single person playing the game on their client, their computer, their Xbox, their Switch, they all send messages to one another. And a good example of a game that works like this is Splatoon 2. That uses peer-to-peer networking. Every time you move, you send the information about your movement to all the other players in the game. The next sort of networking is mesh networking. And you can see here, it looks fairly similar, but not quite the same. We're missing a couple of links here. And this is a way of allowing us to have a slightly more robust network when it comes to dealing with NATs. You might have seen, like if you're playing Call of Duty or you're playing Apex Legends or something else, it will be talking about your NAT. Or if you go and take a look in your PlayStation or your Xbox system settings, it will say something about NAT traversal. And that's just talking about how easy it is for other computers to communicate with yours, or how easy it is for other consoles to communicate with yours. Now, because of the way routers are set up, some routers can find it hard to communicate with each other because of the way they're set up. And this kind of setup allows us to have some clients passing messages on behalf of others. We actually used this sort of voice communication, we used this sort of networking, this mesh networking for voice communications on the Crysis series, or it was done via that network topology. Thirdly, then you've got client hosted, and this is where people are a little bit more familiar with this. This is where, in older versions of, say, Call of Duty, that sort of game, you would go and you would select to host a server, and your friends would join you, or random people on the internet would be able to join you. Minecraft is an example of this. If you go and host a LAN game on Minecraft, or just host a game on Minecraft and check the make it online option, that is an example of a client-hosted game. And that's where one client is running the game locally, and it's in charge. It's letting all the other clients know what's happening. And network messages just go between all those other clients and the main one who's in charge. The last type of networking, the last networking topology, is client-server. This is where there's one computer, highlighted in orange here, which isn't running the game for a player's benefit. So in all the other examples you can see here, we have 4 players in the game. In this last example, client server, we only have 3 players in the game, those 3 turquoise dots. And they're going to send all of their information to the server, marked in orange, and it is going to inform all of the other clients about what's going on. And Minecraft Realms is a good example of this. Call of Duty Warzone is a good example of this. Apex Legends as well. Client server is where a lot of networking has moved towards. So, what are the advantages and disadvantages of these different networking types? So, peer-to-peer networking, everyone sends messages to everyone else, as we touched on. What that means, though, is that no one's actually in charge. Now, that makes it really quite hard to write and very hard to reconcile state. And what that means is, if anyone in this network can change things in the world, then how do you know what state the world's in at any one time? Because there are always messages flying around. Some of them may well be contradictory, and it can be really tough to kind of understand what's going on and write code so it's robust to that. Another notable issue with this is that people need the bandwidth. You can see that each one of the clients here, each one of those turquoise dots, every player in the game is having to send information to every other player in the game. So if they want to send information about how they're moving, or if they fired a gun or something, they're going to have to send that information 3 times to 3 other players. And that means there's a higher bandwidth requirement. The big advantage of peer-to-peer, there isn't a server to pay for. And also, technically, this has the best latency of any network. You've probably played games online and heard people talking about latency or talking about lag, and a lot of those games will be client server, where you have to send a message from your client to the server, have it processed, and then sent back or to other clients. And that means that there's 2 steps that the message has to take. It has to go to the server and then get reflected back onto the clients. Peer-to-peer networking, it's just one way, and then the client gets the state. Great, best lag. So mesh networks. As touched on, this is like peer-to-peer, but some messages get passed on. The problem is that this is even harder to write, and still hard to reconcile state, still hard to work out what state the world's going to be in at any given moment. And people do need bandwidth. The other problem is that because you've got some of these clients being responsible for kind of passing messages from one set of people to another set of people who might not be able to communicate otherwise, it's the worst latency. You've got a real problem there. On the plus side, though, there's no server to pay for, and it's better in the real world than peer-to-peer networking is typically. And that's because you can actually get around issues with people's routers and that sort of thing. You can actually make sure that most clients can get into the network and it will work. So the third type of network we touched on was client hosted. And this is sometimes known as listen server or self-hosted. And in this situation, one client is in charge of the world, right? All the messages go through that client. They know what's happening. They are the authority on the state of the game. But what that does mean is that one person needs bandwidth, and one client does more work. They're having to not only run kind of their local state, the things that the local player is doing, but they're also going to have to receive those network messages from everyone else, process them, make the correct actions, validate they're correct, and then reflect that state, reflect those changes back to all the other clients on the network. The lag here is okay. It's not amazing. This client that's been highlighted, they're not completely dedicated to being the server. There's someone also playing the game on there, so it's not as performant as it could be. The good thing about it is this is much easier to write and easier to understand. There's only one place that's in charge of what's going on, and there's still no server to pay for, so that's great. The last type we touched on was client server. This is also known as dedicated server or DEDI server, and surprisingly, that's because there's a dedicated computer in charge. As we noted here on that first slide, there's only 3 players in this game. That orange icon is showing a computer that doesn't have someone playing on it. It is just simulating the state of the game. That does unfortunately mean that you have to pay for it. But on the plus side, it's really easy to write, it's understand. All of the players in the game, they get to do the minimum possible amount of work. They're going to be as performant as they possibly can be. And they don't need to send very much information. They just send information once about what they're doing, and they get the minimum set of information back from that server. Now, while the latency isn't as good as peer-to-peer, the lag, it's pretty good. It's the best of kind of the really usable options. But I said this was about secure games. So what about security? Right, this has just been a primer. This is what are the different variables that can affect this? So how secure are these different network layouts, these different network topologies? So peer-to-peer is utterly trash. Mesh networking is also trash. Client hosted networking is actually just a dumpster fire. Client server, that's good. So why is that? Well, hackers are bad. They can change anything on their client, as we touched on at the start. So we're going to have a little bit of a worked example here. So let's meet Jeff. Now, Jeff is a dick. He wants to ruin your day and ideally ruin everyone else's day on the server. So what happens when Jeff, a bad actor, gets into one of these networking topologies? They get into the game and they're in a position where they can start changing the data, or whether that's network messages or whether that's changing the memory on the local client. So let's look at peer-to-peer. So in peer-to-peer, everyone agrees on what's going on. But in order to agree about what's going on, all of those clients need to know what's happening in the game. And that means that Jeff can see all of the information about the game, because we need to kind of reconcile that state. Now, there are a few different models here. There's kind of shared ownership options where Jeff can just see it. But also there are a number of different approaches to this, where different clients take charge of different aspects of the game or different subsets of, say, the AI or something like that. And in those situations, Jeff can also lie about the things that Jeff owns. So he can just say, oh, no, that bad guy didn't take any damage. Or, surprisingly, I have found all the gold. Those are things that Jeff can do. So how about mesh networking? So this network, we've got Jeff shown as the sickly green color, and we also have another player, Jenny, who's shown as purple. Now in the mesh network, everyone agrees what's going on again, which does mean, again, that Jeff can see all of the information about the game. And that means that Jeff can still potentially lie about all things that Jeff owns, or about what Jeff's doing. But because Jenny's messages are passing through Jeff to the rest of the network, that also means that Jeff can lie about what Jenny's done to all the other players in the game. Or Jeff could lie about what everyone else has done to Jenny. So this might just get the game in a really horrible state. It might enable horrible things like, sending malicious chat messages, that sort of thing. Or it could be, really enabling some cheats there. Now, shining like a terrible beacon above all these is the Jeff hosted network. Now, this is the client host. There is one person in charge of the game, and Jeff is that person. Now, what if you join the game? Now, what if Jeff clicks play and he gets match made, and they don't end up in charge? If someone wants to ruin people's day, they will just quit and restart. And you see this with match-made games, and I've seen this in match-made games, where when you have a bad actor, when you have someone that wants to cause disruption, what they will do is, if they find themselves not being the lobby host, not being the person that is going to be running the simulation on their local computer, their local console, they will simply repeatedly quit and rematch until they find a situation where they are then in charge. And when they're in that state, there is nothing they can't do. And spoilers, they don't have your best interest at heart. Welcome to hell. The last network type that we had was client server. Now, in this situation, the dedicated server is in charge. It holds all the state. And what that means is that because it knows everything, it doesn't need agreement from the other players in the game, Jeff can only see whatever it is the server lets him see. And Jeff can only change the state that he owns. So now, as game developers, it's up to us. So, slight digression here to talk about simplicity. Now, many people will have heard of KISS. And it's an acronym which stands for Keep It Simple, Stupid. And unfortunately, with networking, that does not apply here. And actually, simple, broadly speaking, is stupid. And this is why. The simple way of writing this dedicated server setup, right? We're going for the most secure network topology we can, but we can still do things wrong if we do it the simple way. And the simple way of writing client-server network code is where clients tell us as the server what they've done. They let us know that they've moved somewhere, or that they picked something up, or that they earned this money, or that they killed this monster. But what that actually means is if these are the sorts of networking messages that we allow clients to send to the dedicated server, although the server is in charge of the game state, we're allowing those clients, those players, to have a very direct impact on the world. What these messages translate to once there's a hacker involved is I moved here becomes I can move anywhere. I pick this thing up means that they can pick anything up. If they tell us how much money they earn, they have infinite money. And if they just let us know when they kill a monster, they can kill anything. So we need to think of a different way of handling this network traffic. It's not as simple as just the client telling us what they've done. Instead, we need to switch it around a little bit and make it so that clients tell us what they want to do. Now, that sounds quite subtle, right? But there is actually a really big difference here. And this set of messages change. So I moved here. Instead of telling us where they've gone, they say, I want to move forward. I want to move back. I want to move left. I want to move right. And saying, I picked this thing up becomes, I want to pick this thing up. Please let me. And instead of telling us that they've earned this money, they tell us that they've sold this item. And the really important thing about this small change to how we're thinking about network messages means that it lets us say no. We can say no to Jeff. We can say no to everyone like Jeff. They say that they want to move forward, or they want to pick something up, or they want to sell an item. And we can say, no, you can't move forward. There's a wall there. In the previous model, in a world where people are just saying, I move to this location, we can't say no. The game state doesn't support it. When they say they want to pick something up, we can say to them, no, someone took it first. And when they say that they sold an item rather than they earned the money, we're in charge of how much they get back. Now, that sounds really simple. So like we're done, right? But actually, no, not really. And there are two big reasons why we're not done. One of which is that actually doing this is really tough. Doesn't sound it, but it is. And the other one of which is that there are still ways people can break the game. So what is actually so hard about doing this? And we're gonna take a worked example and kind of try and follow it through to the logical conclusion here. And the example we're going to use is a multiplayer FPS where we shoot monsters. No, not very imaginative. Sorry, bear with me. I did a lot of work in Crysis. There's a lot of shooting things. So within our multiplayer game where we shoot monsters, how do we let other players know that we're shooting and killing those monsters? Well, we send the messages over the network. So this is broadly what it looks like, right? We let other people know that we fired, and then we tell the other players we've killed the monster. This is that original simple way of modeling this. So that's the simplest. Just telling other people that we've killed this monster, and that will work until someone starts hacking the game. So what if someone just sends us a message saying they killed a monster? No firing their gun, no doing damage. Do we just accept that? Because that allows them to just do this, right? They can just go through all the monsters and say kill the monsters, and our game's breaking there. So instead we can force them to take a different route. We can get it so that the client has to tell us about damage, and the server, that dedicated server that has authority that decides what's going on, the server can decide when the monster's dead. So that might look something like this, right? That our client is going to send a message to the server saying, I hit this monster with this much damage. That's loads better. Okay, so now they can't instantly kill all the monsters on the level. They've got to apply damage to all of those. But what if they lie about the amount of damage their gun does? Right, if we look back here, we're telling the server the monster we're targeting and the amount of damage our gun does, they could just lie, right? So they can send us this. So actually, we end up with them just killing the monster straight away anyway. They haven't just called kill. So we're going to have to change that. Instead, we'll get the client to tell us what gun it hit the monster with. And then the server knows the guns, right? It knows how this works. It knows how far away they are. It can work out the damage that should apply. So it looks something like that, maybe. Just tell the server the monster we've hit and the name of the gun we were using when we did it. And that doesn't allow us to cheat in the same way. It is much better. So we're saying hit this monster with a gun rather than that we damage the monster. But what if they don't play ball? What if they don't go along with that plan? They could lie, right? They could tell us any weapon they hit the monster with. And we're believing them at the moment. So we need to take a different approach there. We can't trust that the client is using the right weapon. We can't trust that they've successfully killed the monster. We can't trust that they're applying the right amount of damage. We can't trust that they're using the right weapon. So we're going to flip that around, and we know what weapon the client should have if the rest of our networking is secure, if the rest of our networking is structured in the same way, and our clients are having to ask whether they can do things rather than telling us what they've done. So if we know what they should have, they can just tell us that we fired it, and the server can work out what weapon it is and the damage to apply after that. So in this case, we can now just tell the server that we hit a monster with the current gun and pass in the target monster. So is that it? Well, no, clearly not. There's a bunch more room on the diagram that we had here. So this next step is hitting the monster with my gun. What can they do? What can they do that's a little bit off here? How can they cheat? Well, are they even aiming monster? Right? They're just sending us a message saying they've hit the monster. Are they anywhere near it? Are they? Is there a wall in between them and the bad guy? Don't know. So at the moment, they could do something like this. They could just send us a whole bunch of messages. If someone gets control of the network, or if someone goes and hacks the game, they can just spam a whole bunch of messages down saying that they've hit the monster, they've hit the monster, they've hit the monster, they've hit the monster, and we just go, okay, apply this damage and kill instantly. So there's still a way they can cheat. So next step, let's make the client tell us where they are and where they're aiming. And then the server can work out if they hit anything. Rather than the client just saying, I hit this thing, we'll work out from the information that they give us whether they hit something. So that code might look something like that, right? We've got location and direction, and we'll just tell them that we've fired the current gun. Much more secure. I shot my gun from here. Server can work out if we hit the monster, if we hit a wall or whatnot. Great. But what if they lie about where they shot from? Right? I mean, if they're telling us that information, they can lie about that too. So they could just tell us that they fired from pretty much wherever the monster is, and fire in the direction of the monster. So very frustrating, but we know where the client is because we're validating their movement. And if we're validating movement, we know where the client is, we can get them to not send that, and we can just use the direction they're shooting in. Now, there is one unhappy phase here, which is that because of mouse input, we can't validate direction, right? Counter-Strike, Apex Legends, Call of Duty, all these fast-paced games, mouse input, people can spin through 180 degrees and get a headshot pretty much instantly, completely validly. They're not cheating, they're just really good at the game. And that means that validating that input is incredibly difficult, pretty much impossible. But we can at least reduce the attack area, right? they can reduce down the number of ways they can lie to us. So now they're just telling us the direction they're firing the current gun in, and we work out all the rest of it. But there's still actually another thing, right? They're telling us that they fired the gun. We don't even know they have ammo. Maybe they're on a ladder, maybe they're swimming. So we need to go back to that initial idea, which isn't that the client tells us what they've done, it's that they ask us to do something. So instead of saying that they fired the current gun, the networking message actually becomes request fire current gun, right? And then the server can go and make sure that you've got ammo, you're not in a state where it's invalid for you to do that, the gun's not jammed, or what other reason there might be to prevent you from doing that. So that's one example. That's just shooting a monster with a gun. And you can see there are a whole bunch of ways here where it's very simple, it's very easy to come up with a simple way of networking a piece of gameplay logic that results in a huge chunk of potential attack vectors, call them, right? A whole bunch of different ways of damaging the play experience, ruining the game for other people, or the like. The real problem is that actually that's just one aspect, and every single part of the game needs to do this. The key part is that we want to reduce the surface area that can be attacked from any given call. And it really does mean that one slip up in how any one of these networking messages or pieces of gameplay is being written means that people could potentially break the game. So I have a real example here from a game, not one of the ones that I've called out that I've worked on, but one that I did a little bit of, not exactly contracting on, but advisement on. And this game that I advised on, they let the player choose which of their minions to sacrifice to raise a demon, basically. It just said, like, sacrifice this thing. And there wasn't any validation. It just told the server, I've sacrificed this thing, and you can spawn a demon for me. And you could just choose anything on the client. You could send a message saying it was a bush, it was a tree, a lamp, another player, the game rules, the landscape. Didn't matter, because the client was telling the server what was happening rather than taking this kind of request and validate approach, which is what results in a secure game in general. Now, it's worth noting that unfortunately, there is some stuff that we can't just fix. And that's because at fundamental level, knowledge is power and clients need to know something so people can play, right? The less we tell all of those computers in the game about what's going on, the more secure the game is going to be, and the harder it's going to be for someone to cheat. But we do need to let them know enough about the state of the game to actually be able to effectively play it. So the biggest example here is locations of players, right? If you don't know where the players are in the game, then you can't really play it. Now, I'm sure people have heard about wall hacks and aimbots, and here's a screenshot of an example aimbot from Counter-Strike Go. Sorry, a wall hack even from Counter-Strike Go, and you can see how player in question can see straight through this seemingly solid wall and identify that there is someone on the far side of that. Now, this is quite lightweight. It's relatively easy to do. It's almost impossible to detect someone is actually doing this. They will actually change shaders in the graphics card memory. They will change device drivers, really fundamental parts of Windows, and they will hook those DLLs in a way which means that if you try and look at them to see if someone has done something nefarious with them, the system will tell you everything is fine. And the next step on from just being able to see through these walls is, well, if I've changed my graphics card driver to allow me to see through walls, why not change my input so I'm automatically pointing at people? And that's what an aimbot is, right? It's using the information that you have available in the game to aim directly at people without any input from the player at all. And the most sophisticated versions of these aimbots now, they look like just a USB device on the system. So if you go and look at the system and try and understand what's going on there, see if someone's hacking you, is hacking the game, it just looks like a mouse to the computer. It can't tell there's anything wrong. And they have a large suite of different options that enable them to be turned on, but look as if an actual player is playing. Now, there are a few things you could do to try and reduce the amount of information being sent to a client here and reduce their ability to gain an unfair advantage. But it's not as great as you might think. You look at the screenshot and you think, well, why am I being sent information about these two players? Well, they can cast shadows. They can make noises when they move around. And that sort of second order effect, even if you have the computational power available to identify the fact that these two players can't see each other normally, applying that from the point of view of every player to every other player across the whole game gets extremely expensive on the CPU, takes a lot of CPU power, and that's not something that's always in a huge amount of supply, really. Always in demand, rarely in supply, especially when it comes to larger games, again, kind of Battle Royale, that style of thing, larger open world style games tend to have a much, much higher requirement of CPU. And because of the structure of their worlds, it would be a lot harder to run that sort of evaluation. So, in summary, we've looked at some network topologies and we talked about some of the pros and cons of those network topologies and talked about keeping it simple isn't always the best idea and how we should be writing code that's a bit more secure. Making sure that we are writing code that gets our clients asking to do things rather than telling us what they've done. And hopefully showing that writing secure multiplayer code is actually quite complicated. So please do have some sympathy for big multiplayer game devs, right? You've got a team of maybe a couple of hundred people writing a game and potentially thousands of people trying to find ways to break it. So with that, over to some questions, if we have some. So, Chris, seems like mesh networks are most flexible. Why don't more games use them? Because it's a nightmare to write them and because you've got that really significant latency disadvantage. I had quite a simple example there of a mesh network with just one player where we need to pass messages around through a few nodes. If you end up with a large scale game, if you imagine something like Call of Duty Warzone with 150 people in, and you have a situation where you need to pass through 5 or 6 different nodes to get a message from one player all the way across to another, and then all the way back, that's going to be a giant chunk of lag. You also end up with some quite significant problems if someone decides to drop out of the game, particularly if they are one of those people who is responsible for passing those messages along. Also, of course, the security side of things. So, info from Stevie. Okay, cool. There we go. Questions mostly answered. So, aimbots, is it not possible to check for suspicious behavior on the server, such as very quick, very accurate flicks? Broadly, yes, you can. The problem is, where do you set that? Your realistic goal and the goal that you can achieve is to make it so that the best players, like efficiency, accuracy, is as high as you can make an aimbot. So your aimbots will only make you as good as the very best players there are. The problem is that means that potentially every server you play on has someone who's as good as the best player in the world, cheerfully murdering everyone in a competitive multiplayer shooter. There's also quite a significant challenge when it comes to codifying what that looks like. And also just accidents, right? When I was talking through these situations at work, you often end up in a situation where, if you imagine Counter-Strike's one that I'm most familiar with, playing DE Dust, and there's always a corner, bomb site A, where there is always a person hidden. So half the time, if you suspect someone's in the bomb site, you jump around the corner and you put a round or two into the corner, and you don't need to look. You fire through walls because you have meta information about the game. You know where people like to hide. You know the characteristics of the people you're playing against, and the weapon, the topology of the site. So something that in one context is a deeply suspicious act, like I'm going to pull out a gun and I'm just going to shoot a hole, shoot through this wall in front of me for no apparent reason. That's deeply suspicious in one situation, but with the right context, that's an extremely sensible thing to do. If you imagine you see someone jump into a crate and then you shoot them through the wall of the crate without being able to see them, that's fine. If you never saw them jump into that crate and you walk around the corner and just put a round into the crate and kill them, that's deeply troubling. So trying to encode that information, trying to understand, the difference between consistent behavior, which is at the far end of plausible, and people who are lucky, unlucky, or just plain good, it's really, really difficult. And as Chris said, how do you decide where that line is drawn? Because there's always going to be someone who's a lot better than anyone you think should have a right to be, right? There are some people who are absolute monsters out there at first-person shooters. And although I'm talking a bunch about shooters, this applies across a huge number of different games. AI-driven cheat detection, is that a viable strategy in the future? So I believe some people have experimented with this. Part of the problem is that your set of training data is quite hard. I think one thing that talked about historically was looking at people's patterns of movement to try and work out whether they had wall hacks. So in a fast-paced deathmatch style shooter, where people are spawning at different places in the level and the objective is to kill as many of your opponents as possible, having that information about where people have appeared in the level has the potential to really change how someone's playing. But again, it's very difficult to actually take into account all of the context that you might have. For example, you might well have a couple of people playing in the same room on the same multiplayer server. And I can turn around and look at someone's screen, or I can collaborate with my teammate to let them know what's going on. And that could produce effects in game that would look, again, deeply suspicious because it doesn't have the context of that outside information. In fact, it probably looks suspicious to most observers, even though there's nothing inherently wrong with doing that. Right. Any other questions? Not looking like it. Okay. Thank you very much for your time. It's been a pleasure having chat about it. Hopefully I didn't mess anything up too much because this is the first time I've given this particular talk. So if you're going and writing some multiplayer games, try and make them a little bit more secure. Thanks, folks.